everyone. Thank you all for coming here today for our seminar. Very happy to host Dr. Max Lee here with us today. Dr. Lee is an assistant professor of aerospace engineering at the University of Michigan, and also has courtesy appointments in civil and environmental engineering, as well as industrial and operations engineering, so many affiliations. And his research is in air transportation systems, airport and airline operations, advanced air mobility, network systems, as well as optimization and control. We're very happy to have you here today and learn more about your research. So with that, feel free to take it away.
Thanks so much, Jackie, and thanks for coming out on a rainy day. I guess it's rare here. So super happy to be here with y'all to chat through sort of two projects that we've been working on. Basically around the theme of there's a lot of unknowns, uncertainty that happens when you try to operate the air transportation system, and how can we do a little bit better to find out a little bit more. So first, I wanted to just level set everybody because I know I'm already starting to throw terms like air traffic control and air traffic management at y'all. So just in one video, and I'll sort of illustrate the difference between the two terms. What you're going to see in the next slide is actually a FAA, we're going to pick on Dallas-Fort Worth for a bit. So on the next slide, you'll see an FAA radar replay of kind of the airspace right around Dallas-Fort Worth. And what you're going to see is a particular day where we didn't quite get the weather prediction quite right. So air traffic management kind of fell through in the sense that there was more demand trying to get into Dallas than there was capacity at Dallas to actually accommodate them. But then you'll also see kind of air traffic control kind of stepping into the rescue, because essentially the whole point of air traffic management is to manage the demand capacity balance to try to make it so that air traffic controllers aren't overwhelmed. But sometimes we don't do a great job at it, and we see how air traffic controllers kind of handle things much more tactically, trying to keep aircraft separated. So in my mind, I'm always like, air traffic management is you are managing the demand capacity across an airport and airspace, the entire US. Air traffic controllers are keeping metal separated from each other. Okay, those are sort of the fundamental difference. So here's Dallas. Sorry, it's a little rainy, but what you see is the thunderstorm starting to roll in, and you essentially start seeing all of these arrival aircraft get told to do holding, to wait for this thunderstorm to pass. And in fact, if we wait a little bit longer in the video, what you'll soon start to see is as the thunderstorm kind of slowly crawls out of the way, air traffic control starts releasing some of the aircraft back into Dallas, but they realize that the thunderstorm is moving a little too slow, so they start doing these like squiggly S vectoring patterns to try to slow them down so that they stay separated and that we can accommodate them at Dallas. So ideally, if air traffic management had done well here, we wouldn't have these holding in the first place. We would actually have these aircraft waiting at the gates, not even having taken off. So we would have delayed them on the ground at their origin, not kind of in this situation. So hopefully in one video, it's a good sort of separation in your mind between air traffic management and air traffic control. And the two things that I'll talk about research-wise, we'll look at both of them. Yes?
But isn't the air traffic control system responsible for the ground stops that you just talked about?
So that's
who tells the airlines to do that?
It's actually the air traffic managers. So so there's actually this command center at an hour and a half outside of DC that actually is managing kind of nationwide demand capacity balance. And they tell airlines, hey, we're going to have an issue at Chicago, so we need to stop traffic going in Chicago for the X amount of hours. So it's actually traffic managers, not controllers who are doing
I
this.
think for most
Yeah.
people, that distinction is completely,
Yes, I think so controllers are the ones telling the airplane like, hey, turn now so that you can maintain separation. Managers are, I don't want to say back office, that's kind of rude, but they're the ones looking across entire networks, entire systems, trying to make sure that capacity and demand are balanced. So, and then, I won't belabor this slide too much, but essentially, I've always been of the opinion that some delay is good because it shows that you're using the system to sort of the amount, the level that it was built for, but we don't want excessive delay. So a lot of what the two projects that I'll try to cover today is all about how do we remove excessive delay from the system. Okay, so the first project has a very fancy title, but what it boils down to is how can we help these three pretty different sets of stakeholders? So the people flying the airplane, the people trying to maintain separation and make sure these airplanes are flying safely, and airline dispatchers who are working. So these are the people hours before your flight ever leaves. They're making your flight plans, and then they're continuing to communicate with pilots, with air traffic control to follow your flight through its journey. So how can we help them work together to actually reopen airspace? So I'll talk about what that means when the weather is bad. Okay, this is essentially what the first part of the talk will be focused on. So it's more air traffic control centric. What do I mean by when airspace is closed? So how we organize the airspace is, so here are the New York airports. It's kind of hard to see, but you can kind of see the state outlines. So these are the New York airports, and there is a very complex piece of airspace called the New York Terminal Area, or N90, that surrounds the New York airspace. It's complex enough that we don't really just let people fly in and out wherever they like. We actually constrain the entrances and exits out of this complex airspace into what's called departure gates. So these are kind of invisible points in the sky that we route air traffic through. And what happens commonly when you have a weather system moving in is you'll see air traffic control working with air traffic management to say, hey, there's this big system moving here. We're getting a lot of airplanes that are deviating around this big system. I'm going to shut down these two gates. So now you see a little stop sign, basically denoting that those gates have been stopped, and you can no longer file flight plans through those two gates. Okay. And you see some other stop gates here. So sometimes a gate is stopped because there's a weather pattern sitting right above it. Sometimes a gate is stopped because the jet routes coming off of that gate has weather sitting on top of it. Okay. So why do we do this? Airplanes, it's not because of rain or whatever. It's actually because a lot of this convective weather, there's a lot of moisture. There's a lot of wind holding that moisture up. So it's extremely turbulent right around the area of this convection. And we don't want aircraft traveling through that amount of moderate to severe turbulence. So we will close these gates to make sure that airlines will basically file flight plans and take alternative routes. This is all fine and good until you keep something closed for too long. So why might someone keep something closed for too long? Basically, our radar systems are only so good in the sense that maybe one of the gates could have been opened by now because the weather has either dissipated enough or there's a gap that you can shoot through the weather. But we don't really have sensors, radar systems at 12,000 feet, 15,000 feet to know exactly the conditions at the gates or at the jet routes downstream. What is the best way to actually ascertain that condition? It's to send a flight and see how the ride was for that flight. And that's exactly what we mean when we say these so-called pathfinder operations. They are particularly critical at airports like the New York airports because obviously they're very busy, but more so, they don't have a lot of concrete. What do I mean by that? if you have closed departure gates and people aren't departing, they hold on the airport surface. And at some point, you have no more room on the airport surface and you have to stop arrivals. And it becomes this very kind of cascaded problem through the network. This isn't New York, but this is Seattle at it's a video. So this is Seattle at a day where some of the departure gates were closed out of Seattle. And essentially it becomes this gigantic queue on the ground because some aircraft can't depart because their departure routes are not clear. They're still the departure gates for that route is stopped. Okay. So the question is, how can we use flights to actually go and see if a route can be opened earlier rather than later? So this is commonly done in operations today, but it's done in a very ad hoc way. So there's not really any sort of modeling, decision support, optimization that goes into when should we send out a Pathfinder, who should be a Pathfinder flight, and who is kind of the best option to be that Pathfinder flight.
So the Pathfinder flight has got a lot of people who hate turbulence on it, then they're in trouble, right?
Yeah, so it becomes an interesting question of like, do the pilots want to accept this, right? So we end up having, so what we essentially end up developing are like, what is the pilot's utility model? What is the air traffic controller's utility model? And what's the airline dispatcher's utility model? And how do we try to put some rigor into this selection process? Because what happens today is, okay, something happens today, then tomorrow people fight. The airlines say, why didn't you open that gate 1 hour earlier? And the air traffic controller said, why didn't you help us out with a Pathfinder flight? Why did you reject all my Pathfinder decisions? Right? So having sat in enough of these national system review calls, which happen daily on weekdays, the question that I started to work with, and this is a NASA funded project, is how can we put some numbers behind these arguments essentially? It's how, can we actually say if Delta had been 10% more likely to accept a Pathfinder flight, then that would have translated to a 15% chance of that gate being opened earlier. So that's the kind of models that we were looking to develop. Okay, so again, just to kind of start helping you build some intuition for what are the different incentive structures here. For a pilot, the disincentives are bad turbulence, and a bumpy ride, a potential ride where it's turbulent enough that you would do what's called a deviation. So you would ask to actually reroute around the road. That's a disincentive. The incentive is if you're stuck back in the queue and you have a potential 60-minute surface queue waiting before you can depart, if you accept the Pathfinder operations, you could cut the entire queue. You could actually depart as a Pathfinder flight. So those are sort of the pilot's incentives and disincentive structures. What are the incentives and disincentives for air traffic controllers? So for controllers, the disincentive is if you give a Pathfinder to someone and you have to make the effort of having to reroute their taxi paths and reissue clearances, there is an inertia to actually offering a Pathfinder flight to someone. So that's sort of the disincentive for the air traffic controller. The incentive for air traffic controller is a potential system-wide benefit of having a gate that's open 1 hour earlier than it would have been and letting you release the surface queues at your airport. What's the benefit for airlines? So for the dispatcher sitting at the airlines, the dispatcher sitting at the airline is, and this is reflected in our utility models that we write, the airline dispatcher has pretty much the same disincentives and incentives as an air traffic controller, except that they don't care if a Pathfinder flight helped out in a United Airlines flight if they're at Delta. Right? So they kind of have a airline-centric incentive rather than a system-wide incentive to decide if a Pathfinder is worth it for them or not. Okay, so what we did was we said, well, there's sort of no model out there at all, so can we build just a simple Markov chain to at least kind of try to decompose this problem into a more understandable formulation and use that formulation to build an optimization model to say, when do we offer a pathfinder to who, to which flight? So that's where we started, and then we went into utility models and then the actual pathfinder sequence optimization process. I'll kind of elaborate on the key details that'll thread its way through up until the sequence optimization part. But essentially, working with air traffic controllers, we broke down pathfinding to a very simple 4-state Markov chain. There's nothing secret going on here. It's just a simple Markov chain where you have a gate. So they're also called airspace fixes, but this is basically a gate. Okay, so a gate is closed. And if the weather condition is like sufficiently bad, you would just keep that gate closed. You wouldn't even try to make a pathfinder selection. Okay. When the weather conditions are sufficiently good, you would make an offer to someone to be a pathfinder. If someone accepts, right? So now this has to do with basically what are the pilot's incentives, what are the airline dispatcher incentives to issue and to accept pathfinders. If someone accepts, then pathfinding is initiated, and pathfinding can either succeed or fail, right? So a failed pathfinder is a flight that starts to try to probe this departure gate, realizes it's too bumpy, and have to deviate. So we would consider that a failed pathfinder flight, and that would kind of punch you right back into the gate closed situation. So this is sort of, we wanted to boil it down to like what are the main states and what are the simplest components that we can look at for this type of problem. Okay, so we did some kind of just validation work where we said, okay, if the acceptance rates are high and the conditions for asking for a pathfinder is good, we should expect that to give us the highest chance of opening a gate. So we just wanted to make sure that like all of these steady state probabilities made intuitive sense to controllers, to pilots, and so on. And we were also able to get basically FAA logs that actually log like how many pathfinders did we try, who accepted, who declined, to actually parameterize some of these p-values, these probability values. So even at this stage, we can at least say, a historical data in the past, here were the probabilities of acceptance, of non-acceptance. The kind of fuzzy part is what defines a good probability for even being able to offer a pathfinder. So that part is fuzzy, because controllers can't really even tell you that, of like, when do they feel confident enough to send a pathfinder, when do they not? So that part is a little, but we were able to at least show that intuitively the probabilities work out the way that we would expect them to work out. So I'm kind of going a little fast. I wanted to get to the sequence optimization part, but essentially, like, these are sort of the kind of intuition checks that we were looking for. Okay, probability of gate open increases as the probability of conditions amenable to pathfinding opens, and while the probability of gate closing decreases. So we're just doing some intuition checks that this simple Markov chain model is giving us the right intuition. On the utility side, so as I said, the three kind of stakeholders here are air traffic controllers, dispatchers, and also flight. So these are sort of the three groups that we need to somehow get to work together as best as we can. Sometimes air traffic control can say, hey, we need a pathfinder flight. Sometimes the pilot, not the pilots, sometimes the airline will actually suggest, like, hey, if we send out a pathfinder right now, this would be really beneficial for my fleet, is kind of the airline initiated pathfinding. So right now, this process is super ad hoc in today's world. Sometimes people get busy, they don't ask for pathfinders, and the gate stays closed. So we wanted to say, how can we actually bring some systems thinking into this entire process? So what we did was we said, all right, what is kind of a simple utility model that we can think of? If you think of each flight as an agent, then a flight can either accept or decline a pathfinder offer. And for that flight, there are different costs. So there is a participation cost, which is generally best described in terms of fuel. So if you do accept the pathfinding flight, do you have the right extra amount of fuel in case if something goes wrong? Okay, so you need to be fueled and ready for it. That's a participation cost. The failure cost is, potential deviations, potential extra fuel burn, kind of this more less, kind of harder to capture cost of loss of passenger goodwill if people are like thrown around in the cabin too much. So that's sort of the failure cost in some sense. And then the reward is maybe you get a reduction in your departure delays because you got to skip the line and depart first. Okay. So we have this, again, pretty simple utility model that if you accept a Pathfinder offer and you succeed, this is sort of your utility. And then if you don't accept it at all, then the utility is zero. This is for the flight. This is for the pilots. Yeah, and then we wanted to model essentially like, could we look at sort of deterministic pilots versus sort of more, pilots that are a little bit harder to know exactly what they'll do. So we used a pretty simple Lojer model where we said, if this beta parameter is larger, then essentially it's a bit of the decision boundary of whether you accept or not accept is a bit fuzzier. So we wanted to capture a little bit of what might be sort of pretty random human decision making because each pilot is going to be different. Each pilot that you ask is going to be different. For the air traffic controller, the utility model looks something like this, where essentially you're trying to decide, this is kind of the main reward that you get, is how much delay reduction do you get across your entire schedule if the Pathfinder that you offered is successful. Okay, that's really this is really the main parameter driving the reward for an air traffic controller, and it's modulated by things like, well, I have to now kind of disrupt my ground control queue because I need to take this flight out, I need to route him, to the departure position. That's actually not something that ground controllers like to do. It's better for them if they just sit in line and wait their turn. So there is a control effort on actually allocating a Pathfinder. And then for the dispatcher, as I said, these two equations they're literally the same. The only difference is that for dispatchers, they only care about the airline-specific departure benefits. Okay, and there are kind of specific airline-specific things like maybe the dispatcher knows if I can get this flight out now, the pilots won't time out and they can continue operating this flight. Whereas if I don't get this flight out and it's going to take a 60-minute taxi delay, pilots time out, they pumpkin out, and we have to return it to the gates, right? So this is not going to be necessarily in the air traffic controller's utility. It's going to be at the airline. It's going to be at the airline. There's also rules like the Department of Transportation's rule about not having you sit out on the tarmac for more than 3 hours. That's going to factor in at the airline dispatcher's desk, and that's going to factor into their utility model. So with this formulation, and again, we can so we have an ITSC conference paper that we published, and we just have a preprint kind of on the journal version that expands on all of this. So we can go. Happy to send you the paper for the details, but I'm trying to give you some of the highlights. So we can do things like what we call the worst case analysis. And the reason why this is called the worst case is this is a situation where air traffic controllers, airlines, and pilots uniformly agree that they don't want this to happen, because usually they know that either this is just a really bad weather day or the gates are going to stay closed for like way too long. So the worst case we define is, what if all of your flights reject offer? So you can't even initiate the process. Again, you can from those utility models that I was showing you, you can of course calculate calculate out what is the rejection probability, and assuming independence across flights, which is a big assumption because it's not always true. Of course, the actual rejection probability you can compute analytically. Again, assuming independence. That what I mean by that is if one flight says no, that's not going to impact what another flight sides, which is not true. Or it's somewhat true across all the airlines, but if you look airline specific, it's not true. So, what we kind of did one step beyond this is we said maybe some pilots are just more receptive to saying yes, and maybe some are more receptive to saying no. So we wanted to look at, again, this is a stylized model, right? We wanted to say if in an airline there's sort of two groups, one is more receptive pilots, one is more rejected pilots. What is the proportional mix that might get you past the threshold of the worst case happening? So we were essentially trying to get at this question of if you can somehow incentivize a pilot to say yes more, and again, that part is tricky because what does that really mean? Do you really want to reward them with money? Because that would seem like you're rewarding them to take riskier flights, right? So there's sort of interesting questions of what does incentivization mean in this case, and we don't really get into that in this paper. We were just trying to we were trying to arrive to results like this, where this is the proportion of pilots that are more rejective. And let's say if you were aiming for the worst case happening no more than 10% of the time. So with a 10% chance, everybody rejects. What does that mean for the most number of rejective agents you can have in your fleets? Okay, so past more than 64% of pilots being rejected, your probability of having the worst case happen skyrockets past your 10% threshold. And if you have if less proportion of those pilots are in your fleet, then you keep your worst case happening at lower than your set 10% threshold. So we were trying to get to results like this to begin to put some numbers to say, if more pilots had been a little bit more receptive to a Pathfinder operation, look, we can now say how much more, at least with respect to the fleet of your pilots who are agreeing or disagreeing to be a Pathfinder. Again, that was under independence. We've done a couple of other cases where the chances of someone else saying no becomes greater if someone already said no. So we've done a couple bit more of these dependence when that's in the journal paper. But the independence case is sort of at least the nicest equation wise to look at. Sequence optimization. So this is really, I'm biased, but this is really where I think the fun comes in, because right now, it's basically up to the controllers to kind of make mental calculations of who I should ask, specifically which flight in my lineup should I ask to be a Pathfinder. So we wanted to ask the question, given a simple model like this, can we build a optimizer that actually tells you, hey, if you ask this fourth flight has the most maximized system-wide benefit. So the problem looks something like this, where you have, let's say, a sequence of flights that are lined up on the taxiway, and the question is, what is the contribution of each flight to the overall objective? And again, this is a multi-objective problem because the air traffic controller's objective is different from the flight dispatcher's objective. So those are the two perspectives you can take. We actually look at them as completely decoupled problems. So we either solve this as from the perspective of an ATC, or we solve this from the perspective of an airline dispatchers. Future work would be really good to combine these two perspectives. Okay. So we solve them separately for now, and we say, all right, well, in this case, maybe this flight is the biggest contribution to the utility, so we're going to give this flight the first Pathfinder.
To whose utility?
So the pilot's utility function doesn't change between the two optimization models, but for one optimization model, the objective function maximizes the utility of the air traffic controller. Another optimization maximizes the utility of the airline dispatchers. So we actually all present them as separate.
So which one are you showing us here?
Oh no, this is a notional example. This is just this is not the actual results yet. I'm going to skip this because we've already seen this slide. I just wanted to remind people of the three stakeholders in this problem. So this is the air traffic control optimization. So it becomes a nonlinear integer program where we are looking, so this here is exactly the utility function of the air traffic controller. So this is for a system level benefit and the burden of changing up the Pathfinder offer. Okay. The reason why this objective looks a little nasty is because essentially you need to go through this entire sequence. So there's sort of this combinatorial number of people that you can ask, right? The first K people have to say no in order to get to the next person. So that you make offers sequentially, and you're looking at a line of aircraft that you're making offers to. And all of these constraints essentially just become, like logic constraints. So you can only give a flight one offer and so on. So these are sort of logical constraints that need to be enforced.
So X and Y are,
So yes, so basically X is do you give an offer to plane I at position K, at the offer position K, and Y is an auxiliary, right? Yes.
You don't have like the dynamics in here.
What do you mean by dynamics?
The fact that like the planes are going to be moving along the taxi lane, right?
Yeah. So we don't have dynamics, and we absorb all of that into this budget constraint B of how much effort it takes you to route somebody. Yeah, so there's no sort of like movement. It's really just an offer optimization. And then I'll also flash. So this is air traffic control initiated. This is dispatcher initiated. Basically looks the same with the exception of this now changes to the airline utility, and now all of these offers are constrained to the set of flights in your own airline. Right? So the structure of the problems are exactly the same. It's just what is the feasible set? What is the set of agents that you're making offers to, and what is the to your question, what is the objective function structure?
but so the P's are the probabilities of acceptance, right?
Correct. Yeah.
But those are not known, are they?
So they're calculated through this right. So we have this logit function for like whether a pilot will accept or not accept, depending if they're receptive or rejective pilots. So
Right, but for implementing the thing, how do you know that?
in the real world, there's a couple of things we could do, both of which are controversial. So you could look at historical behavior, right, for that particular pilot. This is actually something that when I gave this talk in to Japanese airlines and air traffic, they're like, great, like for every pilot, like tell me what their what is their rejected? Are they rejected? Are they receptive? Here we have very strong pilot unions, and we like it's actually even hard for me to get individual crew data. Right? So we're very protective when it comes to crew. So the question is, can this still offer benefit if we can only say something at an aggregate level, like Southwest pilots are more likely to be receptive versus American Airlines? So at a group level, can we say something that's useful? Yes.
I'm a little bit confused. The P accept has a subscript I. Is that like you design a special function for each agent, or they share the same function?
It's specific for each agent I or each flight I. Right. And it's not just flight I, right? It's each flight I for position K. So it's also because for each position, there's a different reward that you get. Right. So if you're a pilot and you're already first in line, you're kind of like, well, like I don't have that much to gain even by taking a Pathfinder offer. But if you're the 17th pilot in line and you're like, hey, I think I could actually do this, your reward is different, not just based on your probability of acceptance is different, but it's the probability of accepting the Kth offer, given that you are currently in a specific place in the queue. Yes.
You have these two objectives, two problems. My question is like, right now, who does make the offer? Is it the ATC or is it the dispatcher for the
both? So right now, both of these, they sometimes. So you raised a really interesting question because sometimes dispatchers, without consulting air traffic controllers, will be like, hey, I think you should ask to be a Pathfinder. Oh, here's the flight plan. Go ask. Sometimes air traffic control will independently, without consulting dispatchers, be like, it'd be great if you can take this Pathfinder offer, go ask your dispatcher to route you a new plan. There also are conditions, are cases where air traffic controllers are communicating with dispatchers and they jointly develop a plan, which would be outside of the scope of both of these models because they're solved independently at the. So the question is, how do you join them together? Honestly, this is already nasty enough to solve as a, and thankfully I can say stuff like, well, there probably won't be more than 40 aircraft in line at any point in time. So I'm not solving this across like thousands of agents, right? It's really just the max that it will ever be in the queue on the airport surface. So we can solve these brute force, we can solve them through heuristics and, they give, but this is not a convex. This is not a nicely structured problem, unfortunately. Something that my student is currently thinking about is like, can we actually relax this into like a nicer looking linear integer program? Probably not. So we're trying to think about ways of relaxing this. Not because we want to use this for civil aviation. Oh, I shouldn't say that. This is still civil aviation. But the whole, this whole project, we're also interested in thinking about if and when in the future we have a bunch of autonomous airplanes that are operating in our system, those airplanes are going to have to make decisions amongst themselves of like who is going to be the pathfinder, who goes and probes the weather, right? So in that case, you actually might have more than 40 agents. You might have hundreds that are trying to make kind of this collaborative decision. Anyways, that's going beyond the scope of this talk. But I wanted to show you, so basically we have these two optimization models, and what I wanted to walk through is sort of, we developed a pretty simple discrete event simulator for actually trying to simulate this with a real set of airline schedules. So how this event simulator essentially works is you have a set of flights that, pull them from FlightAware, that's your initial flight schedules. They're going to join basically a runway queue, and you compute the schedule to see what are all the PIKs and what are all the parameters, the rewards, the utilities, and then you run either. So again, I'm not solving these two problems jointly. So we literally will either solve it from the air traffic control side, or we solve it for the airline dispatch perspective. And then we either, if someone was picked to be a pathfinder, they take off or they don't take off, and then we update the current state of the queue. I think I asked my student, yeah. So we just, this is a very simple video. So this is just a little visualization of what the discrete event simulator is doing. So if you didn't have a pathfinder and you could never open fix2, so fix2 here is the fix that was closed, and flight 10 was decided to be the pathfinder by the optimization algorithm. We just wanted to show that with fix2 open compared to without fix2 open, that you get a faster flow of traffic, essentially. We could certainly make this much prettier, but we tested this on a case study at New York, JFK, and the reason we picked New York is they are one of the heaviest users of Pathfinder operations today. So we said, oh, maybe they would stand to benefit the most. What we did was we looked at a set of 30 flights across an hour. So during this hour, there was convection at one of the departure gates. Okay. And out of those 30 flights, so you always have to do a little bit of a down select, because this is an operational reason. If the gate that is closed is east of JFK, you will never give a Pathfinder offer to someone who's flying west. So you would only give Pathfinder offers to people who are flying in that direction or approximately that direction. So you down selected, but the dirty laundry is it didn't really work with 30 flights because it was too computationally expensive for the optimizer. So we said, okay, well, actually, I don't think it's even legit to even look across 30 flights, because air traffic controllers, dispatchers would never do that. They would never assign a Pathfinder out east for someone going out west. Okay. So in some sense, dirty laundry, in other sense, relatively realistic assumption. Yeah, so eastbound departures only, and we assume that we're not messing with the runway configuration. We assume that we're departing just on one runway, or on one set of. This was the actual schedule that we used. I guess it was an hour and a half. My apologies, hour and a half. Historically, some random day that we picked in September that had some weather. This was a set of flights that was scheduled to depart in that time frame. And the aircraft that are highlighted in bold, which I realize are a little hard to see, but the aircraft that are highlighted in bold are the Pathfinder eligible candidates. So we only optimize over this sequence, not over the entire schedule. And so what we first looked at was given this discrete queuing system, so these are flights, and this is which offer would you give them, and would you give them the first offer, the second offer, the third offer, and so on. So uniformly, for example, for the amount of benefit to the system, all of these flights basically have give the same amount of reward. So this is not the result of the optimization. This is pre-computing the parameters for this optimization problem. Is what is the benefit that each flight would contribute to the entire system? That's what this one is. And then so something like this would be like, what is the burden on the air traffic controller for giving a Pathfinder to this guy who's back in the line? So this is the highest burden flight in order to get them out of the bottom of the queue. So these are just some parameter studies, and what I really wanted to get to. Yeah, so most of the parameters increase when offers are made earlier in the sequence. That kind of makes sense because the pilots, utility-wise, they're getting the most benefit if they get to leave the queue first, especially if they're bottom, like farther down in the queue. What was interesting is, so we looked at what was the results of who gets picked to be Pathfinder if it was air traffic control initiated versus if it was dispatcher initiated. By and large, for air traffic control initiated Pathfinders, more or less a first come, first serve sequencing was fine. This is because the dominant parameter in the objective is a system-wide benefit. So for a system-wide benefit, it makes sense that the earlier you can get something out with least effort, the better it can be. Okay. Now the question is are these three flights, are the pilots amenable, right? Are they receptive? Are they rejective? That would become a factor if we had better ways to kind of segregate these different pilots by how likely or unlikely they are to take an assignment. What was more interesting was if you look at all of the different dispatcher perspective, it no longer necessarily became first come, first serve. It became, first of all, where are my flights in this queue? And how do I think about which one gives me the most benefit depending on which offer that they're given? And I think this highlights a challenging practical question of how do we reconcile this with this? This is what we need to do. This is what happens all the time is there's some negotiations that's happening between, hey, this is who we want to send out as an air traffic controller for the biggest system benefit, but dispatchers are going to have different utilities of who's the most useful, right? Yes.
It's not clear. How are the flights ordered on the vertical axis?
Sorry, so the flights are ordered based off of their position in the queue. So this is the first flight that's currently like basically at the runway threshold. Yeah, sorry about that. Should have mentioned. Yeah. So that's what I meant by this diagonal is essentially first come, first serve according to your position in line. Right? Whereas for the dispatcher, of course, it's a strong function of which sets of these flights are even pathfinding eligible in the first place. So where we are with this research is we have shown this model, it is acceptable by airlines, air traffic, and we can run it across 14 flights. We can run it across a small number of flights. the next step is to actually run a giant set of case studies on a giant list of historical days where there were Pathfinder operations that happened and say, had you select, oh, yes.
So the intuition is that the controller has no trouble letting the first guy go as the Pathfinder, doesn't have to reorganize the queue.
Correct.
And that's why the thing goes down like this.
Basically,
Right.
Yep, that's right.
But the people at the back of the queue have the most benefit from being a Pathfinder because otherwise they're,
So I think
so from the airline's point of view, the guys at the back of the queue are the ones most likely to participate.
so it really,
Exactly.
so that intuition is correct, but it depends on the actual initial condition of the line, right? Like if you were an airline and you had someone at the beginning and the back, the question is, well, if the folks in the back might have a higher likelihood of accepting the offer, and the people in the back here are more likely to time out. Like if I can get them out right now, they're less likely to time out. Then you would see this. But there's also some utility of still sticking with people in the front, because people in the front, you would still they would still open up the path and let everybody in the back out. And it could be the case where the folks in the back don't have a crew timeout problem. So if all of your flights are equivalent, then maybe you actually want to send out someone in the front because it's less burden for the like there so if we go back to the dispatcher utility real quick. Let's see. Yeah, so the dispatcher does have a cost as well in terms of picking flights, because they know if it's later on in the queue, air traffic is more likely to say no, right? So then we do impose a cost, but this cost is not as high as the actual air traffic controller's cost of routing someone in. So if you got rid of this chunk, then it would be much more last come first. It would be like straight up just that opposite diagonal going up. So we wanted to kind of moderate a little bit. Yes.
Another factor is if the flight is late,
Yes.
how bad is that? Maybe a flight that's supposed to get in at 11 p.m.
Yes.
gets in at 1 a.m. and that's not great, right?
Yeah.
So you want to avoid that type of thing.
Exactly. So that would get baked into the flight's reward, into the pilot's reward function and the airline dispatcher reward function, because, well, I guess from the dispatcher's perspective, of course, they don't want late flights, but sort of even if a flight is late, it's not as big of a red flag until it's so late that it would misconnect passengers or misconnect crews. That's when that's when their cost function jumps. And that's really when they become the most worried in some sense. So in some sense, what I'm showing you today is like basically just the model formulation and a check that sort of the model intuitions give us good stuff. The next step, which I think is probably the more challenging step, is how do we show that under what circumstances do we benefit from decision support on when and where a Pathfinder is issued versus what we are doing today? Like, how can we show that there is a gap between what we do today in terms of pathfinding and what we could potentially do? Now, this probably won't be uniformly better because there's a lot of assumptions that we bake in things, right? Especially when it comes to rejected and receptive pilots. So we are actually talking to Singapore and Japan to do something similar, but they would actually give us specific like pilot utilities, right? Which would be interesting to see, especially to compare. Hey, we know pilot receptive, rejective. Here we only know at a group level receptive, rejected pilots. What do we? Okay, I realized that I completely missed. I mistimed this. I have like a whole second, which is a slightly more complete research. But that's okay. I think this Pathfinder one is interesting because one, if you've ever flown out of a top 30 airport in the US and there was weather surrounding the airport, you may have benefited or not benefited if pathfinders weren't used successfully from one of these operations. Second, I think it's the sort of the more kind of air traffic control one. The other research that I wanted to talk about, it's a little bit more the air traffic and I'll just spend like 1 minute just giving you the sky high summary of this. But essentially everything that we talked about in part one, was air traffic control, right? Was on this control part. Part two was actually asking the question of, could we have done strategic traffic management, holding people at the gates? Could we have done that in a better way? And that essentially boils down to a overly conservative, not conservative enough balance. What do I mean by that? If you're overly conservative, you give everybody millions of ground delay minutes, you're not going to have a problem at your terminal airspace, but these are also unnecessary. You're starving the system of demand. We don't want that. Not conservative enough is saying, oh yeah, I know there's a problem, but you can go. And then you might incur airborne delays. Okay. There's a sort of an optimal in the middle where you're just right. Okay. But the problem is getting it just right requires you to have pretty good idea of what the capacity is going to be at your arrival airport. We are now in the age of machine learning, so you can imagine some black box ML algorithm giving you a prediction of the arrival capacity at the other airport. We wanted to ask the question, what if the machine learning model is wrong, but it's not only wrong in terms of the specific distribution, but what if it's wrong distributionally? Like the machine learning model said, the capacity is going to be 40 aircraft per hour and it's a Gaussian distribution center at 40. What if in reality it's actually a bimodal distribution? So how do you make decisions against distributionally wrong predictions coming out of a machine learning model? That was the premise. The actual research ended up being, how do we solve these distributionally robust optimization problems faster? So this was kind of the more OR-y part, where we essentially do these kind of fancy two-phase benders plus L-shaped techniques to speed up these DRO solvers. So it kind of became less on the air traffic side and more on how do we solve DRO faster. But anyways, yes.
Does this modeling approach take into account the fact that ground delays keep gates occupied and interfere with arriving flights?
So or
do they put the planes on somewhere else away from the gate in a ground delay?
So in either case, if the ground delay is so bad that you're holding up arrivals, that's like a really bad, like you don't want that situation. We actually also account for the current departure rates at an airport. The current arrival rates at the airport that is being impacted. So right, the ground delay program is always, you have some impacted airport and you have people feeding it and you say stop feeding it. We also account for the people feeding the aircraft at the airport feeding the other. So we do account for bad enough of a gate hold that impacts arrivals down the chain. That is.
In practice, are planes moved away from the gate and then held on the ground? Has that ever happened?
No, because that would activate DOT3 rules. Like the moment you're off the gate, and you start accumulating DOT3 delay minutes. So in practice, if you're ground delayed and it's so bad that you're holding up the gate for an arrival, what they'll do is, if the arrival hasn't left yet, they'll hold that arrival. So you kind of get this chain of holding. Mm-hmm. If the arrivals have already come, the airlines will do their best to shift gates. So they'll do a gate change if practical. If not practical, they'll let the airplane land and they'll let the arrival aircraft wait at a penalty box until something clears. So you never take the ground delayed aircraft off the gate. You just let it wait so far. But so sorry I didn't get to talk about this, but I'm happy to send the slides. This is again the more ORE part. But let me pause here and see if there are any questions in the last 4 minutes. Yes.
So I don't know much about the operator side of air systems, but I'm obviously a traveler, and when these delays happen, it seems like information and communication is a challenge.
Mhm.
So I'm wondering on the, I'm calling it the operator side, right? Is information and communication also a real challenge?
Yes.
Okay.
So let me give you an example with just Pathfinders. Right now, if a let's say the pilot flies a Pathfinder and it's successful, so the gate reopens. There are like a chain of telephone calls that need to happen between the facilities, between the airline to say like, hey, the gate's open, hey, the gate's right, like and sometimes that doesn't happen, and the airline will continue filing flight plans as if the gate had stayed closed. Honestly, I don't think that's necessarily a research question. It's like, how do we design a dashboard? That no, maybe it is research, but I think there are very practical challenges in terms of information flow, and it's not even just at the passenger level. It's even within the operator spec. Unfortunately,
Yeah, I figured.
Yeah, it speaks to like I flew into a snowstorm the other day, or not the other, like a few weeks ago. And I think it devastated and like airline traffic for the next several days afterwards. It seemed like there was this issue of like, there was no weather at this point, but an airplane that was supposed to fly in to the airport that I was at was also in a place that had no weather, and I couldn't see far enough upstream. And so the airplane that I was supposed to take never came. And that information didn't get received at the airport we were at for many, many hours. And
Yeah.
as a result, now all the passengers had to reschedule flights and whatnot.
Yeah.
And that just
Yeah.
leads to more and more delays.
Yeah.
So is there a process for better communication flow?
Yeah, I mean, I think it's there's both passenger side information that needs to be communicated better, but even on the airline side,
Yeah.
like this like I mean, these are pretty well studied problems in air transport OR, right? Like crew scheduling and disruption management, disruption recovery of crews and of tails and stuff. But implementation is challenging for the airlines, right? And it's a tough business. They're not making that. It's do you invest in the next generation revenue management system, or do you invest in the next generation of IROPS, irregular operations recovery? Usually the revenue managed one wins out, because I think overall, although there are maybe some sparkles of change, because for example, when Southwest was impacted by that 2022 scheduling crisis, the amounts that they were fined in the end equated to about a third of their revenue for the year. So at that point, you're starting to talk about enough disincentives where maybe, actually in Southwest actually did, they did upgrade their crew communication system. So, you could say that that's an improvement. But it's challenging. And so this is why I typically work more at the FAA level. This sounds crazy to say, but right now the FAA is very interested in renovating. Big, beautiful, brand new air traffic control system. It's all the rage. Yeah. Yes.
What's the protocol for when a Pathfinder is unsuccessful reroutes, and then like there's a potential opportunity for another Pathfinder? Is there?
Yeah, that's a great question.
relationship?
That's a great question. So I'll talk about the model and I'll talk about the actual operation. So in the model, that would lower the probability of you asking. It wouldn't take it to zero necessarily, but what we would say is if a Pathfinder failed, the gate stays closed, and you should probably modify the probability of asking a Pathfinder to be a little bit lower, right? Until the weather improves. Because now, I mean, the good thing is if a Pathfinder fails, that's actually good information. That means that gate should stay closed, right? Like you shouldn't maybe try opening it until later on. Right? In practice, if a Pathfinder fails, that can often lead to that gate being closed for even longer than right. So you kind of get this kind of double like bang bang sort of thing where that flight really had to deviate. So we were not even going to touch that gate for hours, and that can you can be gridlocked in New York especially. You don't get a gate open, you get planes on the ground at the queue, sometimes the queues are so bad that someone who lands can't even get off the runway, right? Because there's no space for them to move. So they really don't want departures. In most airports in the world, the problem is arrivals. We want to make sure arriving aircraft can land because otherwise they might have to divert and so on. In New York, it's like, no, you got to get the departures out because if the departures can't go out, nothing comes out, nothing comes in, right? So New York is sort of uniquely special in that case, but they're certainly not the only one. Seattle's pretty bad. For example, SFO is pretty bad. LAX can be pretty bad too, especially if you get in when there's A380s on the surface and they have to close down how. Anyways, so there are cases to make things more challenging. It's called Pathfinders on the East Coast. On the West Coast, they don't call it Pathfinders, they call it probing flights or probe flights. So we actually had like, I remember talking to some of the controllers in LA Center, and they're like, what are Pathfinders? I'm like, oh, blah, blah, blah. I give this whole spiel, and they're like, oh, you mean like probe flights? I'm like, okay, yeah. Okay, sure, same thing. They do the same thing. But that's a fascinating, air transportation is, I think, a sort of a nice little microcosm sort of in and of itself. Thank you for the question.
I think food is here. We can have more discussion while participating in lunch. So I think we can call it here for the presentation side of things, and we can continue discussions
Also,
lunch. Yeah.
sounds
Thank
good.
you so much, Matt.
Yeah, thank you. Leave Zoom.